Good morning, everybody. So, in today's class, we discuss on two more properties of fluid: surface tension and capillarity. So, these two belong to one group. So, if you want to understand surface tension, you have to understand what is cohesion. So, now by this time, you understand that the surface tension is due to cohesion with this uh, note. Just let us take first surface tension.
You must have seen soap bubbles. Have you wondered why they are all spherical? Let us try to make soap bubbles of different shapes. We need soap solution and wire loops of different shapes. We will first take a round shaped wire loop. Dip the wire loop in the soap solution. You will get the film on the loop. Blow the film and the soap bubble will come out. Observe the shape of the bubble. It is round. So a round loop gives a round bubble. Now let us take this irregular shaped loop and make an irregular bubble. No luck? It is still round. We will try with a triangular loop.
All these are small examples of surface tension. Okay. Today's discussion is on surface tension. The first thing is surface tension. If you want to understand, first you should know cohesion. What is cohesion? Attraction between the molecules of the same fluid is called cohesion, and surface tension is due to cohesion. For example, have you observed number one, raindrops, spherical in shape? For example, have you observed, for example, landing and hopping of insects on water surface? How they can move on the surface of water? That means this surface is acting like a membrane. Otherwise, how it will walk? So that means it appears as a sheet. It appears as a stretched membrane. For example, just mercury dropped on ground, what will happen? Disintegrates into spherical balls. Fourth, gently placed pin on water surface. Again, that means the surface behaves like a membrane. Then droplets on lotus leaf. Disintegrate into spherical bubbles. The blood drop spherical. So all this above, from this, what we can understand is the liquid droplets are spherical. This is first thing. The surface supports small weights. This is how, this is due to the property of the fluid surface tension. Where this phenomena is exhibited, surface tension phenomena is exhibited at the interface of liquid and gas. It is water air interface, which is also called as free surface, or at the interface of two liquids which do not mix with each other. So at those places, this property is exhibited, right? So in order to understand this property a little bit better, actually, what we do is consider a container, small tub like a container with liquid. Liquid, we can take it as with liquid water, right? We pour it. For example, I take, so this is a container right? In this container, up to here, water is there. So bottom is water, this is air, this is water. So this is called as interface. Right? That is what water air interface. So now what I have done, if suppose I take a molecule of water here, this is a molecule of water. Here I have taken. If I take a molecule of water here, on right side of it is again another molecule. Bottom is again another molecule. On this side also it has another molecule. On this side another molecule. So this side like this. On every side if I see water molecules. And this molecule is attracted equally on all directions because on all sides of it the same molecules are present. So this molecule is attracted equally in all directions. So let me call that molecule as A. Right? Right. So consider a molecule. Molecule, which molecule? Water molecule. A inside the container. It is attracted equally in all directions due to cohesion. That is what happens there. For example, I consider a molecule here, V. See, this molecule is attracted like this on this side, attracted like this, attracted like this, attracted like this, but above is what? Here is air molecules. So that means at the interface, this molecule is not attracted equally in all directions. This molecule, suppose consider another molecule B, which is on the surface of water. The horizontal forces balance each other. Am I right? Because on both sides it is there. Because on this side also water molecule, on this side also water molecule. So naturally it is attracted equally in both the directions. Right. But coming to vertical forces, see, outside air is there, inside water is there. So naturally, the attraction between the molecules of water is more compared to the attraction between the molecules of water and air. So because of that, coming to vertical forces, there is an imbalance. This molecule B experiences a net. A net what? downward force. What do you mean by that? That means the molecules below it pulls down, resulting a net downward force. So that means the molecules on the surface naturally they will be attracted downwards. But if that is the case, what they will do? The surface molecules try to penetrate into the water, into the surface. So that they go down because there is a net downward pull. Because of that, there is a what you call it as it tries to go down. But will it happen? No. But the molecules below it, the molecules below it, or below it means below the surface, are subjected to compression. The compression effect causes liquid to minimize its surface area. That is minimum surface area. That is why the surface attains spherical shape. Because of this, the surface molecules reorient, reorient among themselves, moving very close to each other, moving very close to each other. Very, very important point. Due to cohesion. The tight packing of surface molecules makes the surface to act as a stretched membrane. However, still they possess a net downward force resulting unbalanced energy. That is why the surface supports weight. That is the reason. This unbalanced energy is responsible for the surface to support any weight. So now let me go into the definition part. Definition of surface tension, basic. Definition of surface tension, right? What is that surface tension? At the surface, please once again very clear, at the surface of contact between a gas, between a liquid and a gas. This is called as water air interface, or between two liquids which do not mix each other. Molecular attraction. What this molecular attraction is called as cohesion. Introduces a force which causes the interface to behave like a stretched membrane, that is membrane under tension. Membrane under tension. This is called as surface tension. So, two important points in this definition for you are: number one, surface tension is possible only at the interface, whether it is water air interface or water and some other liquid which will not mix with water, that interface there. And at that place also, which introduces this force, cohesion, molecular attraction introduces this force. First wording is this interface, second wording is this. This actually causes, basically introduces a force. Because of that force, the surface acts as a film. The surface acts as a stretched membrane. The surface acts as a membrane under tension. So it is the tension at the surface of liquid air. So the interface behaves like a membrane. And that behavior as a membrane is due to the property of the fluid, which is called surface tension. And this surface tension is denoted by sigma. And again, remember, sigma has no meaning. We should write sigma water air. Then only it has meaning. That means when you are writing surface tension, it is at some interface that you should understand. The next point, what are the units of surface tension? Surface tension is at the surface. It is a line force. It is force per unit length is the force per unit length. So therefore, units are Newton per meter. This is one of the important things that you should remember. Then next, what is the dimensional formula? Dimensional formula is always expressed in terms of mass, length, and time. Newton means force actually. Force means basically force per unit length. Force per unit length means force is mass into acceleration by length. So then acceleration is it is meter per second square ml t minus 2 by L. So the dimensional formula is mt minus 2. So this is another thing. So now what are the basically next what you call it as the normally what we call it as the case studies related to surface tension that we will take it up. What are those case studies? Because of surface tension, a pressure difference develops across the surface subjected to surface tension. What are the examples of it? Liquid drops, soap bubbles, liquid jets. So now we need to calculate what is the additional pressure due to surface tension that we have to calculate. So that we work on these three cases because most of the problems in surface tension are number one is theory part people will ask or this problems part. So I will take one by one quickly here. First one, if I take it pressure intensity inside a droplet, a liquid droplet. Consider a liquid droplet. Liquid droplet means raindrop. You can take it as raindrop of radius r having internal pressure intensity. Pressure intensity in excess of outside pressure. That is Pi minus Po is P, small p. Now I draw the droplet. Right. Now if I see this spherical. Now what I will do, I will divide into two halves. This. If I divide it into two halves, how it looks like. If I draw, this is one half. And if you see this, this is again like a circle. Am I right? This is also a circle like. This is how it looks like. Okay. So if I see if the droplet is cut into two halves, then the forces acting on one half, if I consider, there are two forces. Number one is the pressure intensity, which is inside the bubble. Outside is only atmospheric pressure. Remember, when I talk about a raindrop means it is full of water. It is full of water. It is like what you call it as inside, completely fluid molecules is there. There is no empty space inside. All water molecules is there. So if such a body I am taking, the inside molecules actually, what will happen actually, they have their internal pressure actually. So that internal pressure is trying to oppose basically this formation of spherical drop. But the property of the fluid surface tension is such that it makes its surface into minimum surface area. When it is making its surface into minimum surface area, we know the minimum surface area is sphere only. So when it is making into three-dimensional space, anything you take it, that minimum is spherical shape. So that minimum surface area, when it is trying to attain because of surface tension, the inside force, the pressure inside, it opposes it. So that means there are two forces here, right? That's what I wish to mention basically. If the droplet is cut into two halves, if the droplet is cut into two halves, right? The forces acting on one half are: number one, what is the pressure intensity P on the projected area, which acts normal to it. So if P is the pressure, the force is equal to pressure into area. Always pressure acts on the cross section. So that is why it is pi r square. So this is 1. What is the other actually? The second one, the surface tension force, where it acts only on the surface. What is the surface? Now, when I cut into it, this is the surface, right? And this surface shape is what I mentioned, circular. Surface tension force on the circumference, right? On the circumference means on the perimeter. That means sigma into what is the length, because sigma is always force per unit length. What is the length? The perimeter is the length. So now I will show you the forces. Sigma acts like this. So this red. How the other one acts actually? The pressure intensity. This acts normal to it. So until both are equal, this try to acquire the minimum surface area basically. These two forces equal and opposite at equilibrium. Equating, what will happen? P into pi r square is equal to sigma into 2 pi r. So what is P is equal to? P is equal to sigma 2 pi r by pi r square. So pi will cancel, then r will cancel. It is 2 sigma by r. Suppose you want to express in terms of diameter, r is equal to, we can write 2 sigma by d by 2. If d is the diameter, so it is 4 sigma by d. So what is P? This P is in excess of pressure inside. That means internal pressure minus basically outside pressure. P minus is equal to two equations, 2 sigma by r 4 sigma by d. This is one case study. What is the other case study? Basically, the second one we will take it. Soap bubble. Soap bubble, if you observe it, it is hollow. Fundamentally, if you observe the soap bubble, naturally, the soap bubble is fundamentally, it is hollow normally. So the inside is a hollow inside. That you should remember. Then basically here what will happen, the we will have actually in this case there will be two surfaces in contact with air, one inside the other. It is not like a raindrop where inside is completely molecules, but it is like hollow actually. Or otherwise, you see it also when you are soap bubble, you just make a bubble on the ground and then just break it and observe on the ground. You see two circles, one inside the other. So how it looks like if I see, for example, so this is the half of the bubble, right? Or better, this I can show you on the ground I am talking about. So on the ground only I will put it this better. So if I put, this is the bubble actually, right? How it looks like, this is one, the water, and again inside the other what we can see is this is also, we can see there will be two things actually, one inside the other. So that means how the forces will act, this will act one, you understand, the outer one, and again the inner one is another. So both are sigma. This is sigma, this is sigma. Whereas the internal pressure is, this is P1. So the difference is same like above basically. First one is the pressure intensity, which is acting normal to the pressure intensity P, acting normal to the projected area, and that pressure force is equal to, pressure force is equal to, it is called as force is equal to what we P into pi r square, because always it is area. Whereas the second one is the surface tension force. It has two surfaces, so that is why it is 2 times sigma into basically 2 pi r. That is the only difference. So now at equilibrium, equating 1 and 2, P into pi r square is equal to 2 into sigma into 2 pi r. So again P is equal to, here if you see 4 sigma pi r divided by pi r square. So pi will cancel, r cancel. So it is 4 sigma by r, it is 8 sigma by t. So P is equal to Pi minus Po. This is what our notation is equal to 4 sigma by R or 8 sigma by T. This is the second case study. What is the third case study? Liquid jet. Liquid jet means if when you are taking a pipe of water and how the pipe of water is coming out, if you observe it, that is what we mean by liquid jet actually. So what is the pressure intensity inside? So what we are calculating is what is the pressure intensity, what is the additional pressure intensity. That is the way which we write it. Because Pi, my internal minus outside, additional pressure intensity inside the liquid jet. This is what we are calculating. Again, if you consider, for example, a liquid jet, just because normally it is cylindrical. So this is cylindrical, right? So let us say its length is L you are taking and it is the radius is R. you are considering diameter is naturally d. So if you are considering like that, again, if you take one half of it, if I take one half of it, for example, so naturally, this is one half of it I have taken. So if I take one half of it, generally how it looks like, half I am taking, cut it actually vertically. So half of it I am taking. So how the surface pressure inside will be, the pressure will be acting actually, if I take it, the pressure will be acting inside. This is how the pressure on the projected area. Whereas if I take it the other way, basically, for example, how the surface tension will act is, this is the surface tension along this length, because surface tension is always a line force. So only along the line, this is one line, this is another line of the what we call it as cylindrical jet. So if I take it like that, then first force is, what is the pressure intensity? Pressure intensity P on the projected area. Per cylinder, you know what is the projected area. It is that force is equal to P into projected area is L into, basically it is 2R, that is projected area. And the second one is the surface tension is sigma into 2L. So at equilibrium, equating these two, P into L into 2R is equal to sigma into 2L. Therefore, P is equal to, this is Pi minus Po is equal to sigma into 2L by 2R. So it is L into L will cancel, 2 will cancel. It is sigma by R, R 2 sigma by D. So P is equal to sigma by R or 2 sigma by D. So these are the three case studies. So with this, we have completed the surface tension topic.
Like, share, and subscribe. Hit the bell icon for more updates.